Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture number 26. So, today we are going to discuss a new topic called fluorescence anisotropy. So, before discussing this fluorescence anisotropy, let us see what is called the polarization of light. So, this fluorescence anisotropy is the effect of polarized light on emission. So, this is called the fluorescence anisotropy. So, what is light polarization? We know that light is a transverse electromagnetic wave. Here I have the electric field oscillating right with a characteristic frequency of this light that is depending on the wavelength of the light, and I also have this magnetic field also oscillating like this way, and both are oscillating perpendicular to the direction of the propagation. Here is my direction of propagation. Direction of propagation. Now, if you see the normal lights, right, the normal lights, then the normal lights can be represented as the electric field oscillating in all the direction, right. So, in this case you see here like this is a kind of spring, and I am actually oscillating this spring in the vertical direction here, in this vertical direction, in this direction I am oscillating this spring. What you can do, you can also oscillate the spring in the horizontal direction like that way. So, here the spring is oscillating like this way. So, depending on your wish, you can oscillate the spring either in the vertical or horizontal or any direction in between them. If you consider the light, the normal light source, and this is the electric field of this light source, right. Here is my electric field, then the oscillation of this electric field could be at any direction either in the vertical or horizontal or any direction between the vertical and the horizontal. So, the electric field here is either in this direction or in this direction or in this direction, like all the possible direction is possible. So, this is the direction of the oscillation of electric field. Direction of oscillation of the electric field. But if you can do something that the electric field is only either oscillating only in this direction or like in this direction, right. What is the direction of propagation of your light? Like out of this plane, right, out of this plane, this is the direction of propagation of the light. So, then you will get a different type of light, and that is called the polarized light. In the first case, you will get the vertical polarization, vertically polarized light. So, electric field is oscillating here the direction of the propagation, and in this case you will get horizontal polarization or 0 degree. So, electric field is oscillating in the horizontal direction towards horizontal and here this is your direction of propagation. But you note that in both the cases this oscillation of electric field is perpendicular to the direction of propagation, but in this case this is vertically oscillating and in this case it is horizontally oscillating. So, as I said, for this unpolarized light, here the direction of oscillation could be anything, like this is my electric field as I said. So, it could be in this direction, it could be in this direction, and all the directions are allowed or possible. However, for a plane polarized light where it is oscillating only in this direction, here it is only oscillating in this y direction, you see. So, then this electric field is only oscillating along this x y plane, but it is not oscillating along any other plane, right. So, this is called the plane polarized light. So, this is a special type of light from this normal light is unpolarized light and this light is a plane polarized light, or sometimes we also call it a polarized light. Okay. It is possible to convert the unpolarized light to the plane polarized light by using some kind of optical device is called the polarizer. So, if you use a polarizer is an optical element, right. So, it is a kind of optics, then if you pass this unpolarized light, it will become the plane polarized light. See, after passing through it will become plane polarized light, and depending on the orientation of this polarizer. So, if it is oriented like this way, you see this is the direction, some directions which is written in this polarizer. If it is oriented like this way, then what you get? You will get this kind of polarization, but if you change the orientation of the polarizer, if it is now oriented like this way, then when a unpolarized light will pass through. So, how I denote the unpolarized light? By putting this arrow in all the directions, that is how we are going to indicate this is unpolarized light. But when this light will pass through this polarizer, now this polarizer is oriented in a different fashion compared to this one, then the light which will come through is like this. Again it is a plane polarized light, but it is not vertically polarized light, this is the horizontally polarized light. So, in this case this is a horizontally polarized light. Okay, with this thing, now let us see what will be the fate of excitation when we will use a plane polarized light compared to the unpolarized light. So, before that I also have to tell you one important thing which is known as transition moment. Let me draw one molecule, let us say this is the S0 state of this molecule, ground state. This type of diagram we have seen many times in the early part of this course. This is my S2, and when you excite the molecule from S0 to S1 state or S0 to S2 state, right, that excitation is possible only when, right, it is allowed transition as well as the available energy will match with the energy difference between the two states, right. That is what we have discussed. Now, along with this transition, there must be some change in the electronic distribution in this molecule, and in this case this electronic distribution in the molecule can be designated as the transition moment of this molecule, of this excitation. Let us see if I write this as transition moment, then this transition moment is defined as the transient dipole resulting from the displacement of charges during a transition. So, in most of the cases this transition moment is represented by vector quantity in this molecular frame. Okay, let me show you this molecular frame of anthracene over here. So, just I am drawing the anthracene molecule, right. So, I can excite this anthracene either from S0 to S1 state or S0 to S2 state. Now, for this S0 to S1 state and S0 to S2 state, there will obviously there will be a change in the electron density of this molecule from this HOMO to LUMO or HOMO to LUMO plus 1, HOMO to LUMO plus 2. Okay, so, see here this is the anthracene molecule, and for this anthracene molecule for the S0 S1 transition or S0 S2 transition, that means the change of this from HOMO to LUMO, the electron is going either from HOMO to LUMO for this S1 state or HOMO to LUMO plus 1 depending on the situation. So, that means what I wanted to say is that there is a change in the electron density, that means there is a change in the charges, distribution of the charge. So, that can be represented as a vector that in which direction the charges are changing. So, in this molecular frame, and if you plot that, what you are going to see a line associated with this transition. Let us say this is that my S0 S2 transition. So, the transition moment is along this molecular frame. So, this is my transition moment and this is along this direction of this anthracene molecule. If you excite from S0 to S1, so that S0 S1 transition is along this direction in this molecular frame. Okay. I take a different molecule and this will be different. Let us say I will take a coumarin dye . Let us take I have taken this coumarin dye. In this case, the direction of this transition moment are different. For the S0 S1 is over like this way. This is S0 S1 transition moment. For S0 S2, it is in like this way. This is S0 S2 transition moment. So, depending on the molecule, the direction is different. And if you use a polarized light, plain polarized light, right, that means the electric field is oscillating in a particular direction. Right. If this is the propagation of the light, electric field is oscillating like this. Not all the directions are allowed directions. Right. So, only in one direction, it could be like this. So, now if I have unpolarized light and if I have a polarized light for the excitation, what is the difference? So, to show this difference, let me take a sample having this kind of fluorophore. Okay, before that, let me write one sentence over here, right, which just see this sentence and I will explain this later on in more detail. So, here I am writing the fluorophores whose transition moments are oriented in a direction close to that of the electric vector of the incident radiation are preferentially excited. Let me explain this. So, here I said the fluoropores, see here, these fluoropores means either this or that or some other, whose transition moments are oriented in a direction close to that of electric vector of the incident radiation. So, here the transition moment, which transition moment? When I am exciting it from S0 to S1, then I have to talk about this transition moment. If I am exciting from S0 to S2, then I have to talk about this transition moment. So, for a particular excitation either from S0 to S1 or S0 to S2, let us fix that for the time being. So, let us say consider that I am exciting from S0 to S1. So, for this molecule, for this anthracene molecule, what I will write? For this anthracene molecule, this is my transition moment, and now let me replace this molecule only with its transition moment. So, this replace with only this, that means this is my anthracene molecule and this is my transition moment. Which transition moment? S0 S1 transition moment, and if I draw this molecule, I can tell that the molecule is oriented like this way. Now, if the molecule is oriented like this way and if the electric field of the incoming radiation, right, incoming light is along oscillating along this way, then the excitation is more favorable than if the molecule, the transition moment is oriented like this way and the excitation is like vertical. So, here you see this is 90 degree and here it is 0 degree. So, that is what I am telling here. The fluoropore whose transition moments are oriented in a direction close to that of the electric vector of the incident radiation. So, here the orientation of the transition moment is close to that of electric field, this electric vector of the incoming light. So, this is my excitation light source. Excitation light source. So, in this case I have this oscillation, right, this electric field oscillation is very close to the orientation of this transition moment. In this case it is not. Now, let us take a situation that I have many molecules in solution. Let me draw one sample chamber over here, and here you have taken several lots of these fluoropores in a particular solvent. Now, the distribution of these fluoropores within this in this solvent will be random, and the relative orientation will also be random, right. So, that is in one word called isotropically oriented, right. What I want to say is that this is in the ground state, right. So, the some molecule will oriented like this way. Whenever I am drawing it like this way, I am drawing its transition moment, as I have already explained. The shape of the molecule could be like this, the shape of the molecule could be like this, but its transition moment is along this So, I am just writing the transition moment. So, here I am most worried about how the transition moment is oriented in this solution. So, as I said, the transition moment can orient like this way. There is no restriction. So, that transition moment could also take this orientation, it could also take this. So, I am going to have a random orientation of the transition moment throughout this solvent. So, there is no restriction of that, and obviously some like this. So, all these different orientations are possible. It means that the orientation is isotropic. The orientation is isotropic. So, I will just write here isotropic orientation. Now, consider you are exciting your sample with unpolarized light, right, with unpolarized light, and I am drawing this unpolarized light like this way, which is understandable to you. So, this is the excitation light and this is unpolarized, that can be described by all these different arrows over here. So, this is unpolarized light. That means, I have the electric field oscillating in all the possible direction, which all of them are perpendicular to the direction of propagation of the light. So, one of these orientation will find its counterpart in the unpolarized light. This one, let us say this one will find this one is very close, the orientation is very close. This guy will find that this one, the orientation is very close. For this guy, you will find that this one orientation is very close. For this one, it will find that orientation of this one is very close. So, all these molecules will eventually be excited from the ground state to the excited state, as all this transition moment will find the electric field which is oriented along it during the excitation. So, eventually probably all the molecule will be excited from the ground state to the excited state. This is the extreme situation I am talking about, right. Now, consider that you do not have this unpolarized light, but you have this polarized light. So, if you have this polarized light, let me erase it. Now, if I have this polarized light, then the light polarization means the electric field is oscillating only along a particular direction. So, it is a plane polarized light. So, now consider my electric field is oscillating along this vertical direction. It means that out of all these different molecules which are present in the solution, not everything will going to be excited, because the condition I said, the orientation of the transition moment which is similar to the electric field of the excitation light source, those will be preferentially excited, right. So, in this case, you see here, this guy will be excited, this will be excited, this will be excited, here this one will be excited, here probably it will be excited, this one, this guy, and that is it probably here, this one. So, out of all these molecule, only these green things are excited. So, I have changed the color to the green. Now, if I draw the fate of excitation after excitation means, right, after excitation. So, after excitation, the situation is like that. So, you will have one molecule like this one, right, because all those molecules which have which are the transition moment are oriented along the electric field of the incoming light. So, those are excited and the excited situation is like that. So, you see the excited state, it looks like that all the molecules are oriented in a similar fashion, right. So, it is no longer an isotropic distribution, this is now anisotropic distribution. So, this I have changed from isotropic orientation or isotropic distribution to anisotropic distribution. Now, if you allow some time, right, let us allow some time, then after some time this molecule will reorient, because obviously there is no force, so that this molecule will remain like that. So, they will constantly undergo the reorientation. So, after this molecule will reorient themselves, then the situation will be again isotropic. So, then this probably like this, here like that way. So, it is almost isotropic. So, you see that number of molecules are same, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, here also 1, 2, 3, 4, 5, 6, 7, 8, 9. So, while changing its orientation, it will also come back to the ground state, right, because of its natural lifetime. So, this is like a complicated situation. So, here what we will see, okay, let me talk about the emission intensity here. So, if you see the emission intensity as a function of time, the total emission intensity will decay as per its natural lifetime, but if you see the emission after passing through that special optical element, what I said as a polarizer, this polarizer is, if it is oriented like this way, it will pass the light which are vertically polarized. If it is set like this way, then it will pass lights which are horizontally polarized. So, in this case what we are going to see, just after the excitation, the intensity of light which is polarized vertically, that intensity will be more compared to this intensity. As time goes, the intensity of this one and intensity of this one will be very similar, and that is the subject of fluorescence anisotropy, right. It means that the fluorescence intensity in the vertical direction is more compared to the horizontal direction. Horizontal direction, vertical direction means the polarization of this fluorescence emitted light, right. So, the intensity along the vertical direction is more compared to the horizontal direction at the initial time, but that means the system is anisotropic. Because the system is anisotropic, all the molecules are oriented like this way, that is why all the molecules are oriented like this way here. So, it is a particular orientation. A particular orientation, that means the emission, right, is also coming out from a particular direction. The light which is coming out of the system, the electric field of this light is oscillating only in a particular direction, that means it is polarized, right. So, this is kind of anisotropic distribution, anisotropic polarization, but as time goes the molecule will reorient themselves to make it isotropic. That means, the light which will come out from this one, from this system after a certain time, then here the intensity of the vertical direction and intensity of the horizontal direction, they will be similar. So, here I can write in mathematical word, here I parallel is high for this case, right, for this case, and I perpendicular is very small. However, after it will reorient themselves to make it isotropic distribution in the solution, in this case I parallel will be equal to I perpendicular, right. And we will continue our discussion on this topic on the next class. Thank you very much.